it's not, okay. Yeah. So when I was asked to make this presentation on empowering European digital on AI sovereignty, I said, wow, I'm a technical guy. I'm not really the right people to talk about digital sovereignty. Then I saw the program, and I see that all the technical stuff were already explained. So you have this morning and yesterday a lot of discussion. So I said, wow, I will do something different. So I will try to reflect my opinion on my history on the topic of sovereignty. And also with all the discussion that we had on this topic into various communities like EPI, which is a community of about 3,000 people on computing architecture, and of course ETP for HPC. So the technical side was of the ETP was partly presented this morning by Craig, so I will not repeat this. So first, when you talk about sovereignty, you need to get a definition. So the classical one is, okay, this is the supreme authority without being subject to any higher earthly power. I say, wow, in our domain, the term sovereignty is nearly impossible. Perhaps in North Korea, but when you are designing computing system, so you see, well, only on the part of hardware, you need CAD tools. Most of them are not in Europe. You need a factory, a foundry. Of course, you could make foundry in Europe, but then you need materials, or something like that are not available in Europe. So I think that for this global sovereignty, I will call it supremacy, in the sense that this is really where you will have all control of the system. And well, it's possible. My organization, CEA, was built for that in supremacy of France in nuclear energy. So that means that you need to have a special organization, political willingness, and a long-term view. So now I will more focus into softer term of sovereignty, a weaker definition. So I will summarize it as, well, having a say at the negotiation table, in the sense that you need to bargain to be able to do what you want into our world. So how we could bargain and how we could have enough weight in the discussion, in the negotiation table, so that we could do what we want and we are not imposed into some technical issue. So of course, I'm a technical guy, so I will a little bit go into more technical side. But first, let's go back to the past. And when you are talking about sovereignty in the 2000s, we didn't talk about sovereignty of Europe. So because this was not a problem. So this is really a recent discussion because of the international context and some political discussion. Our allies on the past are perhaps not so much our allies today, or we could perhaps not trust them as we used to do. So, okay, but in the 2000s, we have sovereignty in Europe. We have a strong business-to-consumer companies, and they were vertical. So Philips, so I worked for Philips for most of my career, Siemens also, in the smartphone, Nokia, Ericsson. We have also a lot of innovation in Europe, and a lot of processor architecture. So ARM, which was created in the 1990s, so initially as Acorn RISC machine, but then this was a joint venture between Apple Computer, so don't forget that they were at the foundation of ARM, of course Acorn, and VLSI technology. We have also the ARC architecture, which you perhaps don't know, but the Intel management engine, that is a very interesting piece. When we were talking about way to the killing switch, you should look at what is Intel Management Engine. It was based on the ARC architecture. In MOS, with the transputer. So in Philips, we have the consumer, Trimedia, and things like that. Then we could say, okay, this was in Europe. How come that now, at least in the semiconductor, Europe is not present? Well, this is very simple. Silicon has a very high value, but very small volume and very lightweight. So transportation is not a problem. So that means that it's better to have optimized part of the process done where it's more efficient for cost reasons, for various things. So, and I remember when I was in Philips, chip could make several times a turn around the world. So because, well, I was working in California, so we make the design. So the masks were done in Japan. The foundry was done in Taiwan. The dicing was done in the east coast of the US. The packaging was done in Kaohsiung, in Taiwan. The integration of the chip to be done in product were done in Europe. And the product were sold in Australia. So you see, that was global globalization. This was possible, unlike for CRTs. So at that time, Philips has CRT's factory, and the TV factories were a few kilometers away from the CRT factories. Why? Because transporting big glasses on vacuum is not efficient. Packing flat panel into a containers or wafers is far more cheaper. So that was one of the reasons. One other reason that we also have, and at least I can almost say within Philips, and I heard that in some other company, that's at that time, about 2000, the European management of this company chose to focus the company where they perform the best, so where they could have big market share. So moving away from the very vertical position. And here we could say something which all scientists, people knows, that the sum of local optimization is lower than a global optimization. And that was why the European semiconductor companies goes into from totally integrated, like Fablight and Fabless. And unlike what you say now are the big leading companies that are very vertical, like Samsung, Apple, and we see even NVIDIA going from the chip to the system to the even application now with their system. So verticalization seems now to be the big step, that we missed that. Let's also make some dream and try to remake the history. In 1986, Philips make a joint venture and spent 58 million in a small startup in Taiwan. And they basically helped this startup by transferring semiconductor manufacturing technologies, intellectual properties, patents, and really helping this company. Philips even providing the first CEO of this company, and this was the first step of the Fablight of Philips. I think that you could guess what is the name of this company. It's TSMC. And at that time, Philips has 28.5% of the share of TSMC. If you go also, again for Philips, because it's a company I know well, so they started in 1984 ASML for because it's not the core activities of Philips, so we need to make a startup and make this out of the company. And so this was a joint venture, so Philips could have 50% of the share of ASML. Here I would say also something else, that ASML has a very nice history because of the constancy of its management to go into extreme UV, while everybody else were abandoning this, even saying it's not possible. So constancy is very important, and you know now, perhaps not for long, because China is shaping up very rapidly, that ASML is the leading company in deep UV that's allowed to make very high-end semiconductors. So all the advanced processors that you have now in our data center and in HPC machine were made with the ASML machine. Then if you remember ARM, so one of the three founders were VLSI technology. So and Philips bought VLSI technology in 1999. So if Philips could have kept its 27% in TSMC, its half in ASML, and its part in ARM, we will not discuss about European sovereignty now. We will have a very strong company in Europe. So that. But it's no way to remake history after, of course. But just to say that a decision that were made at some point has consequences long time after, 10, 15, 20 years after. So the decision that we make today will not be operational tomorrow, but in 5, perhaps not 10 or 15 years. It's not meaning that Europe could not have some kind of sovereignty. Let's take the example of Airbus, which is one of the leaders in airplane, and it's also leveraged. So we talk about Airbus, but Airbus is in fact an ecosystem. So it's very important in Europe to think about ecosystem on all the small and medium enterprises that is feeding perhaps the flagship called Airbus. So I think it's something here. What we could also think is the evolution of the companies in the European. So let's take the 3 top companies in US in 2003. It was mainly automotive companies. In Europe, at least in 2022, and I think it's not so far now, it's mainly also automotive like it was in 23. So in basically 20 years, we still have the same composition of industry. While in US, you see now, it's mainly the digital related companies like Alphabet, Meta, Microsoft, and of course NVIDIA. But most of the digital big giants didn't work on making the final product for the consumer. Most of them are making the technologies allowing others to make the final product, let's say the tools. When we are thinking about Microsoft, except Office, but Office could be also seen a tool to make your paper, your quotation. But basically, Microsoft make an operating system, which is not a final product. It's enabling others to build on top of this to make their own product. Google, so web search is not a final product. It's allow people to go to a web search, so it's a tool. Even if we think about Android, Android is a platform of apps that are done by a lot of other companies. So Apple is the same with the platform and also making computers. So computers are also enablers for you to do whatever you want. NVIDIA, so we say that, some people say that the current AI, no company are making a profit, not OpenAI, not Meta, okay, we could do it, but one company is really making money from the boom of AI, it's NVIDIA, because like for the gold rush, they are providing the tool that allows others to make the product. Intel and AMD are also providing processors, which are not the final stuff. So why they could grow? Because they serve a large customer basis, because all the applications are built on their technology. So and in Europe, it seems that most of the companies are more focusing into making the final product. So of course they have a smaller way of accessing customers. We say, okay, Europe is good between 2013 and 2023. We have doubled our R&D investment. Okay, it's true. So you see, we double it. US also double it, but they started from far higher. And if we compare from the sum of R&D investment of Europe into automotive, computing or ICT hardware and software, well, this is equal to what US was investing only in ICT software. We talk also about China, which starts from far lower than Europe, but they multiply by 8 their investments, so they go very, very fast, and they continue. So I guess that you've seen this announcement that China tried to deploy nearly $100 billion in this AI investment, so from local company and also from the country. One other key point to be sovereign, for me, is to have a vision and be able to keep it whatever is going. So I think it's very interesting to have this long-term vision, because as I told you, it's not doing something for tomorrow, tomorrow in the sense in 3 years from now, that will really be big win in the market. And we also see that we need to work into disruptive technologies. Why? Why? Because when you have an established market, it's the one that didn't know the rule of the market, the established rule, even non-told rule, that could get the jackpot after some time. This is the case with Apple. I remember I was in Barcelona the year of the announcement of the iPhone. So you know, in Barcelona we have this big event about all phones and all providers. And at that time, all the Nokias, Ericsson were laughing about Apple, saying, this company is an ICT technology, they don't know anything about our telecom business, and even their phone is not a good phone, so they will fail. Well, 10 years after, all these Nokia, Ericsson are not here, and Apple is one of the 2 leaders in the domain. We could see the same with Tesla. They enter into the well-established market of fuel-based car with a disruptive approach, which is totally disruptive because the Tesla is not mechanical engine, it's a computer on wheel. So totally different way of approaching the way to make cars. So they also put the innovation now into electric car. And I like to put this, of course, some of the people didn't agree, but I think that when you are an innovation, a long-term innovation, market analysis are not really useful. I really like to quote Steve Jobs that say, it's really hard to design products by focus group. A lot of time people don't know what they want until you show it to them. And he also say, we do not do market research. We just want to make great product. So when I discuss with a lot of European companies, let's say, okay, what the market is needing, we need to make the market analysis to see how we could sell our product. Yes, that's okay for incrementing market, but for really disruption that could change the world in 5-10 years, it's not really useful. So that I mean is also constancy and persistency versus short-term business ups and downs. So this morning we have a talk from CPR that say that they have up and down into their financing. And it's also what were my experience in making a chip. Don't expect the first chip to be a big market hit. Most of the time, you need 3 generations to do it. But how to convince a short-term investor to tell, okay, my first chip is working, but it's not a big hit. We need to make a second one, and then the third one will be really efficient. It's very difficult, at least in Europe. So persistency is very important. Same for the foundry. It's not because you say, okay, we will put billion in making a foundry, that it will be very efficient the day after it's operational. Okay, most of the time it didn't work. Well, I will show you later a slide showing that is not always true. And we all talk today about sovereignty and trying to compete with, this was a startup, a small company in 1995 called NVIDIA. So I really like to go back more in the history of NVIDIA. And Jensen Huang is founder, is still CEO. It's a technical guy, it's not a manager that could move into a cheese factory after or managing whatever. So he's really a technical guy. And he's saying we build in a $0 billion market, spaces where no customer or no competitors, until they become billion-dollar industries. So it's why you need to have a vision, you need to prepare for the future. It will take time. And wow, I will go a little bit in the history of NVIDIA and of artificial neural network. So if you were here this morning, you know that I was making what we call now NPU in the last millennium, so it's 1995. And but after we had a winter of artificial intelligence, so I can telling that you were working on in artificial neural network in the 2000, you will get tomatoes and none of your paper would be accepted. What changed it was in 2012 the result of the team of Inton about ImageNet. So with a neural network approach, they will decrease by, I think, more than 10% the error rate into image recognition. So that was their approach with a small team that you see in the picture with Intan and his 2 PhD students. So one of them is on the left is Ilias's cover. So in Europe, well, he moved to the US, but we have also knowledge in this field with Yann Lequin. So it was a French guy, and also he was at Facebook, but also makes some progress not so far from what Inton did. So that's allowed them, so to Inton, to Yann Lequin, and also Joshua Benjo to get the Turing Award, which is the equivalent of the Nobel Prize in computing in 2018, and Inton gets the Nobel Prize in physics for something which is more computing. So that was also some pure physicists that say, ah, it's not physics like they are doing, or like that, okay. But the more interesting point is this quote from Jensen Huang that says this was the big moment, the big bang of deep learning, a pivotal moment that marked the beginning of AI revolution. But how many other people really look at it? And of course, it's easy to make history after, so it's what Jensen Huang was doing. But he told that at that time, he really thinks that this approach of neural network could revolutionize computing, not having by programming computer, but having them learning from data. So he was trying to push his company into further develop this technology. And he basically said in various interviews that he had to fight nearly 6 years with his board because the board say, wow, why are you going into this neural network? No application. Your company needs to make graphics cards. It's where you get money. But he has constancy, he had this vision. Of course, it could prove wrong. And he was, so the fact that indeed AlexNet was done with a GPU, a graphics card, That's basically we're consuming a 262 petaflop to make this learning in 2012. And I should think that Jensen was lucky because there are another revolution, which was, what could you say, serendipity research. That was unexpected. That was a paper made by Google, so the name of the paper is Attention is All You Need. This paper is the basis of Transformer, so the basis of all the LLM, of all the boom of AI that we are now. The funny story is that even Google didn't take the full impact of this. Another company, small startup called OpenAI, implemented this or make a business before Google. So some of my older friends that are now working in Google DeepMind, this has a strong impact now, and for researchers in Google, it's far more difficult to make publication because now the management needs to check so that not other company could do on this. One other point which is interesting is that this paper was not to invent a new model or a new theory. Their drive was to be more efficient in parallelizing, let's say, recurrent neural networks, so, which is inherently more sequential approach. So they invented the transformer to allow this to be more parallelism and using significantly less time for the training. So also at that time we have Jensen Huang making his first supercomputer and delivering it to the small startup and let him talk about what he said. Could we have audio?
This is my favorite little machine, DGX Spark. The AI supercomputer, we built an AI supercomputer in 2016. It's called the DGX-1. It was the first version of everything that I've been talking about. 8 Volta GPUs connected with NVLink. It took us billions of dollars to build. And on the day we announced it, DGX-1, there were no customers, no interest, no applause, 100% confusion. Why would somebody build a computer like that? Does it run Windows? Nope. And so we built it anyways. Well, thankfully, a young company, a startup, a non-profit startup in San Francisco was so delighted to see the computer. They said, "Can we have one?" And I thought, oh my gosh, we sold one. But then I discovered it was a non-profit. But I put a DGX-1 in my car, and I drove it up to San Francisco, and the name of that company is OpenAI.
So well, of course, I think he's remaking a little bit the history because you know the scientific part of OpenAI at that time was Elias discovered. So where he met a long time ago. So there were some good contact. But it's true that I can tell you in 2018 when OpenAI put their GPT-1 available, nobody except the scientific area found the interest in this technology. But when you see the evolution, so from AlexNet 2012, 8 years after 8 years for GPT-3, it was about 1 million more floating point operation to make the training. And here I show a slide that Craig showed you this morning. And we could have said from the marketing point of view, for the cost of ownership, making such a large language model would not be possible in 2016. Of course, because the paper was not published. But because the cost of ownership, because of the electricity bill to make GPT-3 would have been so high. It was only in 2020 that with new generation of hardware, which has more energy efficiency, so lower electricity bill, that this will be possible. And you see that you could see a strong correlation between the new GPT model. So GPT-4 is one, the upper, which is even more energy efficient. And we can even see now we have GPT-5 because of the new energy efficiency of the system. So cost of energy for training is a limiting factor on the cost of ownership of the system. So looking at the past, we could say, okay, we see at least in AI, we have US and China running, and Europe, we don't know really what will be its position. So is it the conclusion? I don't think so. But we need to find a way where Europe could be back in the game. And the point is that we should not be back in the game trying to copy what US and China are doing. We have a different market, we have a different organization, and we need also to work on what could be the next big wave into the digital industry. So looking forward, trying to prepare not only research, but also company preparing for that is how we will perhaps go back in the race. So I think it's important to learn from the past, so it's why I show you this slide. Also have recs, so basically saying what we did wrong, what the other did well in this domain of computing. Also, one of the weaknesses of Europe is this fragmentation. But as Craig also told this morning, this is also our strength, because we have a diversity. We have a diversity of thinking. We could think of in different way than more homogeneous a population. We have potentially a small and flexible structure like SME. What is the problem of very big companies? So when you are in an established market, if you have an innovation, you will have a tough decision, because if you go into this new innovation, which is a risk, you could cannibalize what were your existing market. I think it's exactly what Google is struggling now with this search engine, with the apparition of artificial intelligence to make search on the web. So, so you need to be able to manage, and which is very difficult on big established companies, because they have an established market. How to make the transition is not easy. When you have a far more flexible ecosystem, this is far more easy. And also Europe has a specific market due to its diversity in culture, in population, in languages. So we should take benefit of it. But we need to work together with a long-term vision and accept to make some concession for the global optimization. Remember, the motto is global optimization is better sum of local optimization. If you only see your own market, your own niche market, without seeing the big picture, you will not benefit from this big market. But that means that you need to take concession to be able to cope with this big market. And this is far more easy in big US company, because you have a CEO that imposes that all the division in the company will work into this direction. Could be also the case in some other country, mainly in Asia, where the state is imposing the direction. All companies need to go into this direction. Not only China, but also Japan, for example. So I think it's interesting to have real important project of common European interest. I will call it, I think it's, the idea is very good, like for the Airbus or things like that. Some of the slides that you could see come from IPIC. And IPIC, we were asked by the Commission a few years ago to make some kind of analysis of the result of European project. We never published it because the results were no good, in a sense that after the financing of the project, all the consortium dissolved it, even the result of the project didn't exist. So everybody gets the money and run. So we need to have this continuation. Indeed, having a 3 years project is very short. So we need to have a continuity more about the idea and things like that. So as it was explained this morning, if we want to make a European processor, it's not in 3 years that you will be a significant part of the market. You need to think for the long term, and it's important to have this drive, this long-term vision on the way to enforce it, on the way to working together, saying, okay, I will make some concession, but I know that in the future I will benefit from this ecosystem. So creating ecosystem is where we could make the difference. As I told you, ecosystem is natural in US because it's a company. Ecosystem are natural in China because it's the government that is creating it. So that's important. And we should not do necessarily trying to copy what the others are doing, because we are different. And let's take again one example about this thing. I will take the example of Japan with their silicon plan. So again here, the Japanese government say to the companies, wow, all you working together, make a consortium called Rapidus to make a foundry. So you have no choice, you need to work together. So this was imposed by the government. And what is the Japanese Rapidus approach? So Japanese like acronym, so that's but the point is that they have, their motto is to have a rapid and unified manufacturing services. So they didn't work for this foundry to make a large volume like TSMC, but to be faster, to have a very short lead time to make IC. The other point which leads to this global optimization is working together between the design and the foundry, and to have feedback here. So again, trying to have a global optimization and not, let's say, the design companies and the foundry and, direct connection. So again, what I was doing, trying to see the global optimization by trying to get all the parts working together. They also use artificial intelligence to help their productivity and to find what are the best points for this. They work into advanced technology that they inherited from US, from IBM, so that was the gate all around, and also chiplet and interposer that I will go back here. But what is the difference? Instead of having batch of 12 large number of wafers, their foundry is based to have single wafer process. So that's allow them to have a very high flexibility to fit with the need of each of the companies that are, of course, different need. But if you have a large wafer, you need to go back into your investment to have a large sale, so selling smartphones, selling billions of GPUs. But if you could make only one wafer, so then you will gain more flexibility. So instead of trying to copy the Taiwanese US markets, a large quantity, very high efficiency, they move into being fast and flexible. And yeah, they might fail, but the first results are quite surprising. So the project started, I think, 5 years ago, but you see on July, during this summer, they get their first device in 2 nanometers. Of course, what they say, and this is a quote from their website, it's only 3 months after getting the EUV, remember, ASML key in the semiconductor industry. So they get it in December, and a few months after, they could have their first thing. So this is, for me, an example where companies working together, trying to think what is different from the market, finding a solution which is more adapted to the market of the Japanese company that didn't have 1 billion of devices, but could be faster, could be more flexible. So that could be a good way. And about chiplet and interposer, you see here they have a roadmap to very large interposer, up to 8 times the reticle size. That could also allow to make a high performance system. Okay. And one point important is, okay, we perhaps not have the manpower, but we need to use AI. So semiconductor is not only trying to make chip for AI, but need to use AI for making the chip. One announcement from NVIDIA that I think few people noticed was their work on what they call QLitho. So it's an adaptation of the CUDA library that allows to make the process for lithography. So lithography is the core of the foundry, and it's quite magic. It's like if you have a hammer of let's say 1 meter wide, you try to put a nail which is 1 millimeter. So with the wavelength that are 100 times larger, you could go very small design. So here it needs a lot of computation. And the point is that it uses weeks in TSMC to make the computation, to make the max. With this approach, it's reducing to 2 days. So again, using AI for improving our computing system is also key. So this morning, I was expecting that Craig will show this, so I will not need to go more detail about the interest of a chiplet on interposer, but it's really how we could go into more SysMore, so a system approach, by using optimized chiplet, using the best technology for each of the functionality, and that also allows this flexibility. You could make a compute a chiplet, like Cyper, an accelerator, and things like that. Depending on the market, you could use different combinations. If you need a high-performance computing, put a lot of memory chiplet, a lot of compute, and perhaps not so much EI accelerator because you are making simulation. But the same chiplet could be used in a car, in a self-driving car engine. Only use different combination of chiplets. So that's allowed to have this flexibility. And this also allows smaller companies to do it, because making a very large chip need a very big team. But a smaller company could make a chiplet. But they need to be sure that their chiplet could be integrated by a system integrator into a system. So that's where we need to do. We need to create this ecosystem of where Europe could do that. And of course, again, when you are making chiplet, you go to different phases, which is disaggregating your stock into basic elements, then reaggregating them into the association of a chiplet of interposer, and don't forget the final stage, which is how to make them into a package. And again, here, we need to have a complete global optimization. It's what we call system technology co-optimization, but it's very important to have this broader view. Again, it's always here. So some advertisement from what we are doing at CEA, but this slide was not really to show you what we are able to do, but to show you the time it takes. We're starting nearly 14 years ago into the first interposer approaches. Basically 6 years ago with active interposer, meaning that on the interposer you have the communication networks on the power converter. And we are working now into photonic interposer. So meaning that the technology that we are working now in research will be in the market in 5-10 years. But we need the constancy, we need to have the companies that are behind us and will believe it. Because yeah, if I want to sell a photonic interposer, we have a lot of marketing because as Steve just said, well, they didn't have seen this before, so they don't know why I would move from my classical approach to this approach. So we spent a lot of time trying to convincing people that this could be a new evolution on the system. And you have a lot of way to make integrator from the 3D sequential integration, where basically you put transistor one on top of each other, so going from the plane to the vertical dimension, to hybrid bonding, so sticking wafer together, to active interposer, and to the packaging, so with all the dimension here. If you want more technical detail, I encourage you to ask or to download the presentation of my colleague Denis, the presentation that he made in the EPI co-design workshop a few weeks ago in Heraklion. So it goes into far more detail. I will borrow a few slides from him, and mainly to focus on some point. So key points are interoperability. So you see, if you want to create this ecosystem, we need to have interoperability, not only at the physical level, but at the data link, at the protocol. So it's why basically UCI is interesting, because it covers the full stack up to the protocol layer. So this is important to be able to have common standards so that several companies could work to create this ecosystem. And you see, of course, the first market will be server HPC, but you see that some other market later could benefit from this, and I told you about automotive market, which could be both in Japan with the Astra approach, and in Europe, see that this could be the future for automotive industry. So, of course, there are projects, as I told you, so this is again the slide from Denis. You see that Europe is not inactive from this. Of course, EPI has a really a point here. So this is again the ecosystem between the mature technology and the advanced technology, where here you see where Europe could have his part. We see that EPI is really active in this area with RISC-V text chip in doing that, but we still need in Europe other parts. So the advanced technology and those that basically that are making the integration. So it's a new job. So it's like the people that were making PCBs, that is integrating all the chiplet into a final product. So it might not be the semiconductor manufacturer that will make the chiplet that could do that. It could be a new market, it could be the same company, but here we have something that needs to be created here. So in the 10 minutes remaining, of course in the keynote, you couldn't do it now without talking about AI. So some people say that we are in the bubble burst period, because if you know the Gardner hype cycle, we see that we are in the going down part in some of the model. But you see that the technology will keep for the long time. Remind you, we have an internet bubble in the 2000s, so a lot of people say, internet, no future, we need to move to something else. So see now, it moves everything. You don't buy CD, you don't buy your video, you are booking your hotel room through internet. So this is the core of the new technology. But it has a bubble, and the surviving companies are the hyperscalers that now are controlling our digital lives. So if we say this, I'm not sure I totally agree with this picture, is a need for compute. And here, this is also something, some discussion I had with some of the colleagues in the Silicon Valley. So you remember I have the separation between sovereignty and supremacy. Supremacy is really to be the unique, to be like the Manhattan Project, so to be the first to make a new technology. And now it seems that in the Valley, they see AI as a two-step. You have this supremacy approach, which is basically under the keyword of artificial superintelligence, based on the belief that we will have AI that could help improving itself, going to a singularity. So from a scientific point of view, it's not a singularity, it's more an eventorism, but I will not go into this terminology. So they really put money on this with this. It's basically what the big companies are selling to the government or to the financing part. It's really like the new Manhattan Project, even that it costs 10 times more than the Manhattan Project. It's really having this very big system, one big load of this very huge model using a lot of compute. So this is here. Versus what are the real need of most of the people in AI? It's not perhaps to try to solve concept or try to optimize a very big problem. It's more making a summary of a text or generating some video or things like that. So it's more in the cloud domain. So, and we see now that most of the high-performance systems are running into simulation, which is digital twin of some process. This morning I talked about destination Earth here. So, is it this very big data center what Europe could do to offer AI to its citizens? And when I mean citizen, is also companies and things like that. I will accept the point about this supremacy. So this is a political issue. Shall we go into this competition to have the ISI? So okay, I will do all this outside of my presentation because this is more a political and need a different ways. Could be other organizations, but I will focus into sovereignty on AI for European citizens. So, as it was told today, inference are becoming more demanding. So, from the discussion that I had with people in the valley, it's between 20 to 50 times more demanding in GPU for inference from learning than from learning. Well, it's not a surprise. ChatGPT has about 5 billion monthly users. Their new thinking model, which is test and compute, iterating on inference, is also demanding more and more. So that drives a new generation of chip, like the Grok chip. Amazon is making their Inferentia, which is a chip dedicated for inference. They also have their Trainium for training. But there are also algorithms. So the algorithms are basically mixture of experts. So what is a mixture of experts? When you are asking something to a big LLM, not all the neurons are active, only few of them. So the idea is to cluster this network into these various experts. And it's only this kind of expert that you activate during inference. And it's not new. GPT-4 was using this. So basically, it used 1/8 of the compute power during inference. That's the number if it runs all the size of the network. One of the well-known examples is DeepSeek R1, because R1 on the 671 billion parameter network only used 37 during inference. So it's why it's cheap, it goes faster, so 8 times less. So this is the mixture of experts. But you have something which is emerging, which is agentic AI. So agentic AI is where you have a multiplicity of smaller dedicated AI that are working together. And also this is often based on a smaller model. And we see now that one evolution is a small model could have very high efficiency on a dedicated problem. They are not general purpose, but you see here that Phi4, which is a model from Microsoft of 14 billion parameter, is better than GPT-4 4.0 into a particular benchmark. So a small model that could run on your laptop, with a lot of memory, but it could run on my laptop, is better than GPT-4 while making this benchmark. Even more surprising here, on a very dedicated benchmark, needing imaging and things like that, a 27 million I say million, not billion parameter, was better than Claude Opus 4, which is supposed to be a very big model. And also here, we could do in Europe, because there are a lot of open weight. Yeah. Most of them coming from China, so I will not enter in this into the political assets of open versus closed, because then I will need another hour to discuss this. But see the policy, the politic of China on open weight is quite interesting. We have plenty of other models that are even smaller. I am personally using on my smartphone the model that you see here, which is a 7 billion model, but using only 4 gigabytes of memory to make analysis of images. So my tickets from the restaurant and things like that. It's running on my smartphone. I don't need a Gigafactory to do it, and it's running quite perfectly. And this is also what the big companies are doing. So Eric Schmidt, the former CEO of Google, said that agentic AI will be the future. Of course, this guy, I think that you know him, also see this is key. Jensen Huang also put this. I show you the video. He was showing this small computer. So this small computer on the GB10, we should be looking at it, because it's not targeting big data center, but more what you could do at the edge using AI locally with this small system. So he's looking at, and of course, Sam Altman. So the idea here is that we could have this small distributed agent that don't need to be centralized in a data server. They could be localized into our host, and they could be very efficient for most of the tasks that you will be asking for AI. And even it could be green. Why? Because if my phone didn't have enough power, it could ask to my laptop, which is sitting idle, because of course when I am using my laptop, my phone, I am not using my laptop. So this could be also helping to increase the lifetime of a system. Some companies are already going it. Apple Intelligence, okay, the results are perhaps not here, but the architecture is quite interesting. You have a various local model, and you have an orchestrator. See, so the interest of orchestrator that selects if the task cannot be done locally, so you first try to do it locally, and if it's not, it's offloaded to more powerful servers using the same underlying technology, the same underlying protocol. So instead of having the big data center that are in the 1 gigawatt, 10 gigawatts, we could do 2 smaller local systems. So Jensen 1 might be ready for the next generation as well. So we need to be careful about this. And also you could run onto your local computer, or even on your smartphone, or even with other smaller devices. So really, this is the edge to cloud continuum, which is going here. And you see, you will have this orchestrator that could delegate things to other devices. Well, my time is nearly up, but I want to finish with one thing. A small thought experiment. There are about 500 million smartphones in Europe. Typical actual mid-range smartphones are about 10 terahertz. So they will be the majority in 2030, because the lifetime of a smartphone is about 3 to 5 years. So current model will be the majority in 3 to 5 times. 40% of them are recharging at night. Nobody is using them. People plug it and forget it. So if you could aggregate them together into a computing fabric, that you have 2 zeta ops. So we are already in the zeta scale area here, without extra investment. Of course, we need to have all the infrastructure, but 2 zeta ops is not what we need. We need more this smaller approach. So what is key again here is interoperability. We need to work together to get this interoperability, not only on the functional but not functional. We didn't have time to go into this, but it's really important that the community, not only the HPC, but the edge, the communications, the security, the payment, work together in order to get this protocol to have this interoperability, so that company could build on this, following this interoperability, a protocol to make their contribution to the global ecosystem. What could be here is like TCP/IP was a way to allow the various operating systems to communicate together. We could have this as the equivalent for the US, what I call orchestration system. So we go from the cloud to cloud on edge to this really more distributed way, which is like an onion skin. You do it locally, and if it's not necessary, you go to the higher step. So I encourage you, if you are more interested, to go to the IP vision, which is called the next computing paradigm here, where you see the orchestration is also a key challenging point. Then partial conclusion here, because I'm not covering the high end here. We should not copy the other solution. We need to work together for something that are adapted to the fragmented market of Europe. So we need to create this ecosystem, not only of chiplets, but also into the more longer term, longer view, which as IP is concerned, is based on an approach that everything is a service, including hardware. And it's the right moment to do it, because we are in a disruptive period due to AI. And as Dave Patterson was saying, in terms of hardware, it's a new golden age for computing architecture. So we have more freedom because we have big challenge ahead of us. So, but we need to act fast. And this is not the strength of Europe to be fast. And as a last slide, well, the future, we have various options. And as Alan Kay said, so Alan Kay is founder of the object-oriented approaches, the best way to predict the future is to invent it. So we have to think about what could be the next generation, working together, sometimes making our own interest a little bit aside for the greater good. So that's my conclusion. We have a way to be back, perhaps not tomorrow, but for the next generation. And it's the right time to work now, because we are in a disruptive period. And it's at this disruptive period that you should take the right decision, because this will be with great consequences in 10, 15 years.